Some security perspective, we need a little bit more of a system security perspective in trustworthy machine learning. What I'm finding is a lot of the work in trustworthy machine learning is mostly done by people whose primary training is machine learning. And I think that's a little bit of a missed opportunity. You really need people who are doing both, who are kind of trained in both machine learning, system security, and maybe even cryptography. And so we need more of these, more of such folks to be crossing over. So for example, myself, I will publish in Usenet Security, Oakland, but I also publish in ICML, NeuraCrypt. And there are more and more people like that. And I think all I wanted to say is that we kind of need even more of that. And as you will see that, you know, in security, we are very good, and cryptography, we are very good at coming up with systematic evaluation sort of algorithms. Like think about, you know, for software security, static dynamic analysis tools, several techniques such as differential cryptanalysis for analyzing crypto systems. So, okay, so this is kind of like, you know, think of me as a lawyer. I'm trying to make these 3 points, and hopefully I can make this case better than these 2 people made for their case. By the way, that joke doesn't land in other places, like, you know, if in some other countries, this, like, I have to change it around. So I'm not going to spend too much time on this. It's basically like, okay, machine learning is everywhere. Okay, I don't need to say that anymore. So our story begins in 2013. If you remember, there were a lot of these articles, even in popular press, basically saying, hey, machine learning is beating a lot of on a lot of tasks, even human performance, okay? Like recognizing objects, solving CAPTCHAs, and, you know, so on and so forth. And maybe this is the reason where, you know, the CAPTCHAs keep, even for a person who's not, you know, who has normal eyes, they're getting harder and harder every year. And this is because a lot of my people in my family are what they call real doctors. So this is more for a dig to them. And my parents still used to think that, hey, why didn't you become a real doctor? What is this Ph.D. thing? So, you know, in 2017, there were articles, they're still coming out that, you know, for some ML models are able to do better at some tasks like reading radiology readings than actually even experts, okay? Now, we all know this, machine learning is used a lot in adversarial settings where there might be an adversary present, or there might be just some incentive for tampering and getting, you know, circumventing the system. So for example, you know, there were this Microsoft chatbot where with some poisoning of data set, it started tweeting some objectionable tweets, which in hindsight didn't, you know, kind of mirrored real life. Then obviously it is used in adversarial, like, you know, autonomous driving, where there could be adversaries present. You know, like YouTube filtering, right? I mean, if I'm somebody putting my YouTube content up and there's some objectionable stuff there, I definitely have some incentive to sort of circumvent that. Okay, and obviously it is used a lot in safety critical systems like drones, robotics, where there might be adversaries present. Okay, so I think that, you know, I was, since I kind of straddled both sides, machine learning, sort of security side and the machine learning side, I was asked by one of the colleagues, okay, what is the DNA? What is different about what is different about security, privacy, crypto mindset than other people? Okay, And so that's kind of like the genesis of this talk, really. What is different about, so suppose you're a security, privacy, crypto, I'll just call them SPC, researcher, and you want to do ML, what do you bring to the, or you want to do trustworthy machine learning, what are you bringing to the table that the machine learning people can't bring? Okay? So let us, so this is kind of the genesis of the talk, and this is the question which I tried to answer, and the rest of the stuff kind of follows from that. Again, as I said, just, you know, if you have a comment, question, feel free to mute yourself and ask. Okay, so this is a very 10,000-foot view. Generally, when we analyze systems in SPC, we have a system as sys. We have some security goal, like an attacker should not be able to forge a digital signature, should not be able to get root access to some server or so on. We have a threat model, which basically says, what can an attacker do? And then we have some security assumptions, which could, systems case could be something like, hey, we have a trusted computing base, which we assume that the attacker cannot tamper with. Some, in crypto case, some factoring problem or some lattice problem is hard, right? So you kind of, even though a lot of security papers or crypto papers, you know, kind of have this inside them, even if they might not formally define all. Okay, and then a lot of our arguments go as follows. If the adversary following the threat model can violate the security goal, sort of forge a digital signature or get a root access to the server, then they must have violated the security assumption. So either have tampered somehow with the trusted computing base, some component in the trusted computing base, or solve or be able to solve some hard problem efficiently. Okay, so the way to a logician would write it is that system, given the adversary, the threat model, if it violates a security goal, then the A violates security as the security assumption. Okay. Now again, I want to say something like in crypto, they're very formal about this, and some formal methods folks are also very formal about this. But even in system security, even if you don't have a formal proof like this, there is some sort of an argument which tries to say what I just said. Okay. Now, given even if these proofs are there, how do these systems or crypto primitives get broken? Well, shoddy proofs and arguments, you know, okay, we're just going to not think about that too much. The threat model is too weak, right? For example, if I have a very strong threat model saying, oh, my entire computer's host is a trusted computing base. Well, that's just you know, kind of ludicrous. And your security assumption is not valid. For example, there are attacks found on trusted execution environments, right? TEs. So if you're assuming, if something is based on that, obviously that assumption has been invalid now. Now, what is very interesting in our field is there are brand new and very ingenious attacks that people find, which makes us go back and revisit our trust model, security assumptions, and so on. So here are the two things that just came to my mind is sort of power analysis of Paul Kocher, right? What he found out is that if you can observe the execution of a crypto system and observe things like power consumptions and so on, that can leak information about the key, right? So side channel analysis. The ROP gadgets paper of Howab Shikar, what he found is that, hey, there are enough existing gadgets, program fragment code in the program that the attacker can piece together to build their exploit. They don't need to even inject new code. right? And if you look at this kind of stuff, it's basically then, went back, and the community went back saying, oh my goodness, we didn't take the account into this. So we had to sort of update all our sort of trust model and security assumption. For example, side channel analysis is now a sub area, right? And there are a lot of papers written on how to handle ROP attacks and so on. Okay, so all I wanted to say is that this mindset of attacks and fix and so on, this cycle is very fundamental to the field. Okay. In fact, some of my papers have been attacked, and I'm sure there are people on the call whose papers have been attacked, and we don't, at least in our community, we don't take it personally. Like, okay, it doesn't become like a spitballing kind of a match. We say, okay, yeah, there was an attack found. Let's kind of refine our system, sort of go forward. Okay. I find, and this is where I will begin, the other communities don't take this same view. Okay. They are somehow take this very seriously. I still remember when Spectre Meltdown came out, and one of the co-authors of that gave a talk in our department, and the computer architects were like, oh, this is just like, this is not very serious, and what is this? They were just thinking that it's not really that important, right? And then now if you look at ISCA and Micro and so on, half the papers are on that subject. So all I'm saying is this mindset that this attack fix cycle, kind of updating the threat model, the security assumption is sort of like the DNA of this field. Now, I had given a similar talk at an event by UIUC, and where Nikita Borisov, and yes, I wanted to embarrass him by putting this picture up. I didn't want to put the professional picture, so hopefully he sees this and he gets irked, and then he and I can hash it out. But he said, oh, but security papers also don't have all proofs, like I just said. Yes, that is true, but they at least have an argument like that, right? Maybe it's in English and so on, but this kind of that, threat model, having a security assumption and so on, is kind of at least part of the whole community. Okay, I am going to stop here because I'm going to now get into more a technical part of the talk. So if you have any questions so far about the setup, sort of the background, please unmute yourself and ask. Or if there are some security privacy people who disagree with what I just said about the security mindset, please feel to comment or sort of, okay. As I said, I'm not monitoring the chat. So if there is something on the chat, you can just unmute and ask me.
Will do, Somesh.
Okay, so here's the game plan. So what I'm going to do is, I was recently involved in 2 papers breaking protocols from some other community, mostly ML folks. And I am going to talk a little bit about those 2 breaks. And I don't want you to focus on the attack too much. And the idea of giving the attack is more to illustrate those 3 points that I had before. Okay, let's do that. So both these papers that I was involved with were in privacy preserving machine learning. Okay, that was the context. But again, as I said, I want you to abstract away from that and think about the bigger message. Okay, so as we know, learning sort of differentially, learning privately, where it doesn't leak information about some sensitive information is a very important thing in machine learning, right? Think about a hospital training something like a machine learning model for predicting who's supposed to get cancer, right? Now, if by interacting with the machine learning model, I can figure out who was used in the training set, well, that is not good, right? That sort of reveals a lot of private information about the patients. So there are techniques such as differentially private stochastic gradient descent, where you can train models with privacy guarantees that don't have some of those issues that I talked about. And I'm not going to talk too much about DPSGD. Just think about DPSGD as a variant of SGD to train a differentially private model that doesn't leak sensitive information about training data. Great. It has great properties. It has been analyzed quite a bit. It is very sort of people still use it. The problem is on realistic models, the accuracy drop is too much. So I've seen accuracy drops of around 20% on something like CFAR 10. So that's like a big downer, right? If DPSGD worked, then the rest of the stuff probably doesn't make sense. But at least at this point, on very realistic models, the accuracy drop is too much. For example, Florian Tramer and Dan Bonnet had a paper in ICLR which showed that with some clever feature engineering, you can beat differentially private deep learning models. If you want privacy, then shallow models might be better. I'm just sort of simplifying the message too much. Okay, so then people have started looking at some alternatives to DPSGD or some other ways to preserve privacy. And one such technique was called InstaHide, which was 2 years back in ICML. And this is the set of authors where we actually broke InstaHide, and it appeared in Oakland 2021. Okay, so let's briefly talk about that break. Now, this is a cartoon version of machine learning. So you have a concept C that labels some pictures, let's say dogs or cats. There is a learning algorithm L that learns a model that tries to approximate that concept, okay? And basically the idea in differentially private or privacy preserving machine learning is, can I make this process of learning private? Okay, good. So the InstaHide is a kind of technique that uses something called instance encoding. And the idea is actually very simple. If I can encode my images using some function which sort of obfuscates the image, and think about maybe gets rid of all the sensitive information, scrambles the image, and then I can still learn on the encoded image a good model, then in some sense, by definition, I am differentially private, right? Because during the learning process, I never used sensitive information. Kind of that's the whole idea of instance encoding. And the idea is if the encoding is private in some sense, which doesn't reveal private information. For example, imagine I learn on patient data and then I remove a lot of the sensitive information. So if the encodings don't reveal information about the input and the computation can be done on the encodings, then by definition, the algorithm is private, right? Because I'm just not even revealing the sensitive information to you. And obviously, this is very useful in multi-party setting. You can imagine two hospitals have their data, they encode it, and then they send it to somewhere where you join these two data, you learn over the joined data. Okay, excellent. If such an encoding system existed, our life would be so much easier, right? So InstaHide is one of those instance encoding techniques. It was it won the Bell Labs Prize. To be honest with you, I read the paper. It's an exquisitely written paper. The paper is very well written. So there is nothing really wrong with the paper. Okay. Just 1 second. Let me just. Okay. So there is nothing really wrong with the paper. But what, before I get into InstaHide, what made me very suspicious, or some of my co-authors also very suspicious, is that if InstaHide was able to get accuracy on some very complicated tasks as well as if the data was not encoded. So that kind of, made us started thinking like, okay, why, there must be something in the encoded images, some signal that is kept so that the machine learning model is going to pick it up. So is InstaHide really private? And then we also answered a similar question: can anything similar to InstaHide be private? Can you have an encoding scheme, not just InstaHide, where it could be private? And so we answered both questions in this Oakland paper. So briefly, what InstaHide works as follows. Very, very briefly, there is a set of private images. So think of this as having sensitive information you want to, not reveal. There is a set of public images. So think about, somebody's Instagram page or Instagram images or whatever. And the first step in InstaHide is to mix them up. So you take your 2 private images and 2 public images, and you just kind of randomly mix these images according to some weights. So this is not a new idea. There is a paper, early paper. So if there are machine learning folks in the audience, there's this whole technique called mix-up. So this is basically you can think about this as the mix-up technique with private and public images. Then there is another one which randomly flips the signs of the pixels. Okay, so you can think of InstaHide as a mix-up step followed by random flipping of pixels. So if you started with that image before, you get this mess over here. Okay, that's our InstaHide algorithm. And what is amazing about this is that, this should be surprising to you, that even with this kind of scrambling, when you learn something over these encoded images, the machine learning models still have a very good accuracy. So I think even on some very complicated things like CFAR 10, CFAR 100, they were only getting accuracy drops of like a couple of %. Okay, but again, this also should make you suspicious and say that, okay, encoding must be keeping some information about the images in sort of the encodings. Otherwise, what is the machine model learning? Think about it this: if I completely scramble the images, like encrypted them, do you think the machine learning algorithm can learn from that? Probably not. Right? So our reconstruction algorithm is a slightly complicated, but basically what it does is we are able to come up with a metric that works on encoded messages by leveraging that the machine learning model had pretty good accuracy. We cluster similar images, and then we are able to recover originals from that. And so let me show you some. So for example, those were the original images, and those were at the bottom are the extracted images from the encoded images that we got. Okay, Now, the attack is fine. I mean, you know, and basically we had a complete break, right? I mean, if you go, there are images out there where we show the original and the extracted. Now, then the second question was, can anything like InstaHide, an encoding scheme, be private? And we started taking a formal view of this. And let me give you basically how we kind of formally model this. So remember, our protocol has two things in it: a learning function L and an encoding function E. And then there is a concept function that labels the images 0 or 1, so cats or dogs. And the adversary picks two instances that are labeled identically. So this is a white fluffy dog, this is a black dog, right? And the challenger then encodes both these images. So for example, in InstaHide, you would encode them using the InstaHide encoding, and sends one of them to the adversary. So you encode the white dog, black dog with an encoding function, and you pick one encoding and you send it to the adversary. The adversary has to guess which one it is. Okay? Now, people who have done crypto, this is very similar to the semantic security game that is done in sort of in cryptography, right? So think about this way, right? If the encoding function was perfect, then the adversary should not be able to guess by more than probability half which image it was. And we essentially have, in some sense, an impossibility result, which goes like this: that if a learning algorithm achieves accuracy better than random, half plus epsilon, on two data for two concept functions, C1 and C2. So for example, imagine our dog cat thing, right? You might have two concept functions there. One concept says which is a dog, which is a cat. The second concept function might say, oh, does it have pointy ears or drooping ears, right? It basically says that if a learning protocol can get better than random chance, better than 50% accuracy on two concept functions, C1, C2, then we can show you an adversary that can win that game that I just showed you by better than random chance, half plus omega epsilon. Okay? So the idea is, if the encoding function keeps enough information for two concept functions C1, C2, then I can as an adversary win that game. So that means the encoding is leaking some information. And the idea is not that hard. What we do is if the adversary security game uses the concept function C1, cats and dogs, then I use C2, like droopy ears, to sort of win the game. And we have a similar one, which basically says that if the learning protocol achieves non-trivial accuracy on two concept functions, C1, C2, then we can get an advantage that is sort of, slightly better, where n is the data size. Okay, so here is a summary. We basically solved the InstaHide challenge that they put together. Well, does this invalidate InstaHide security claims? That's hard to say, because they didn't have any formal falsifiable claim of security in their paper. Okay, and we will get to this point later. Any questions so far? So, by the way, I just wanted you to think about this way, right? We sort of attacked InstaHide, and you should look at authors of InstaHide, right? These are not lightweight. I mean, these are really top-notch folks. So, what did they really miss in this whole thing? So before I get into it, any questions so far? I've been going too fast. You can unmute yourself and just, I'm okay with that. Okay. So there was another paper that, I don't know, there's a follow-up by some other folks, which was called NeuraCrypt by some MIT folks that we also broke. And the NeuraCrypt basically is very similar to InstaHide, where there's a labeled data set and there's an encoding, and you learn over the encoding. But here the encoding, quote unquote, used a key. Okay, so it was a keyed encoding. Remember, InstaHide, the encoding was unkeyed. Okay, and here their whole thing was to hide private health data, so on. But again, the same thing, right? What we did is we, I'll just briefly describe how NeuraCrypt worked, and then we will go to the discussion phase. Basically, the key generation was essentially the random weights of a neural network, and the encoding was basically the output of the neural network modulo some permutations and so on. Basically what they did is, essentially what they said is that the distribution of encodings of two inputs with the same label should be indistinguishable by a computational unbounded adversary. So for example, if I take a cat image, a white cat over a black cat, and remember this key is randomly chosen, and the list of randomized, the distribution of randomization of the first cat is indistinguishable from the randomization of the second cat. Okay, and the threat model is that the adversary sees the plain data set and the encoded data set and must not learn any information about the labels. So that was their threat model. So the authors showed an existence of an ideal encoding that satisfied their property. They showed that this encoding has this perfect privacy property, but the NeuraCrypt sort of approximated this encoding using neural networks, and they sort of relied on this fuzzy thing that, oh, neural networks kind of satisfy this ideal encoding, and that's what we exploited. There were two challenges along with NeuraCrypt, which was that given 10,000 images and their encoding, we have to match the encodings to the images. Okay, so I show you all these clear images. I show you their encoded version, and you need to match which one is which. And then the second one challenge, which we thought was less interesting, was given a set of encoded data, can the adversary find a key that is close enough to the key that we use? So this is very similar to, I show you a bunch of ciphertext for a crypto system, and I say, oh, tell me some information about the key. So we didn't think this was very interesting. So we kind of mostly handled challenge one, and basically we broke it. Okay, that's the short part. We broke it, and we essentially, the high level idea here is we use statistical invariances in different layers of a random neural network, and we are able to train an embedding which is preserved under encodings. Okay, the embedding vectors of the encoded image and the real image are similar. So I'm not going to go into that too much, and that's what we use to kind of break and do the mix and match approach. I'm not going to get too much. And again, we have a thing in the paper where we say that the challenge 2 is not very realistic. Okay, because this is, as I said, this is like finding the key from the ciphertext, which we think it is too strong a definition. And I'm not going to get too much into that. And again, we had theorems here which said, can we actually have an encoding like this? And we have theorems that we show that it's probably not true. Okay, I'm not going to get too much into that. So summary is NeuraCrypt, which was like InstaHide but used keys, is not private. And the challenge too that the authors put out, we don't think is that relevant for privacy. And we had some theorems which said maybe such an encoding scheme is impossible. Okay, now what happened is these papers came out. You should Google InstaHide break, InstaHide attack. It just went into a Twitter war storm. Okay, a lot of back and forth, back and forth, back and forth. And you should also look at this, look at the comments that were in this blog. And, you know, I was actually really surprised by a lot of the stuff going back and forth. I mean, from the paper, you can easily see that we completely broke the system. And what would a security crypto person do? They would sort of say, okay, well, let's go and see how we can refine the method, what went wrong, and so on. And what we found is that the ML community, you know, so a lot of these papers that we broke were mostly, they mostly live in the machine learning space. Somehow, I don't know, you know, it's just like, it's like a disconnect. They're like, oh, well, whatever, the attack is there, you know, and they just didn't react very well to it. And you can, I will not try to say anything here, just go and sort of Google InstaHide attack and look at some of the blogs and so on and so forth. I was personally quite surprised by that reaction, to be honest with you. But so I think this basically shows a big rift in the mindset between the SPC community and the ML community. Now, instance encoding is not an isolated case, privacy preserving machine learning. There are a lot of ML papers that rely on these informal notions, you know, model watermarking, resilience to model theft, robustness of black box evasion. And it's again, I think a lot of this come from because a lot of these things don't have the SPC mindset. And I will have to give a lot of props to one of my co-authors, Nicholas Carlini, who has been breaking a lot of this stuff. And during these breaks, he has been showing that, look, this is how you think about security of a system. And I'm really very appreciative of that. But, you know, we cannot clone 2 million of Nicholas Carlini's to break all. I mean, you know, this is a very busy area. And can we have some systematic way of evaluating such proposals? Okay. You know, a lot of ML security projects release a challenge like InstaHide did. But what I want to do is, let's ask ourselves, what is the goal of a security challenge? Okay. A goal of a security challenge is not as to substitute for a security proof. Okay. It is just a bar, right? I mean, it's like an existence proof. If I can solve your challenge, obviously you are not secure. But if I cannot solve your challenge, doesn't mean you're secure. You know, the burden is on you to have a proof or an argument or whatever, right? So that's very important to understand. I think it's a good idea to have challenges, but we should realize challenges are not it. That's not the end game. For example, here is a basically what is called the in CCA definition for RSA. where you basically, the adversary picks two messages, M0, M1. I'm going to not talk about all the parameters of the game. So this is a game similar to what we talked about before. And the encryption scheme picks one of the messages, M0, M1 randomly to encrypt and send that to the attacker. And basically, you say something is secure if for all PPTA attackers, they cannot win this game with non-negligible probability, right? This is kind of, if you have done a crypto class, you have done these style of arguments. Now, can you prove that a system is CCA secure with a challenge? No, right? Because there is this thing for all attackers of a certain type. A challenger, you cannot just prove that a system is secure by just having one challenge, okay? So for example, if I have a factoring challenge, solving a factoring challenge doesn't mean RSA is not secure. Solving a factoring challenge probably means RSA is not CCA secure, but not the other way around. For example, I'll give you this, right? The Zodiac cipher withstood cryptanalysis for 50 years, but as you know, if you were a security privacy person, would you use the Zodiac cipher to encrypt your messages? Probably not, right? Because it doesn't have the burden of the formal proof. So just because something looks complicated doesn't mean that it is secure. So what were some of the lessons learned, right? We should at least try to have formal definitions, arguments, analysis, proof, whatever you want to talk about when you are working on protocols for trustworthy machine learning. And we need to go beyond attacking your. So for example, a lot of times what happens is people in machine learning, trustworthy machine learning, will put out a proposal, and then they just took some existing attacks from the literature and apply it and say, oh, look, we get pretty good resilience. Well, but remember, in some sense, security is a cat and mouse game, right? If I knew something about your defense, can I somehow change my attack? So these are called adaptive attacks. And we should be trying to do some adaptive attacks as well. Now, we know this is security privacy a lot, that hiding the defense algorithms, security by obscurity, doesn't work, okay? Attackers also have access to archive papers just like you do. But somehow, that mentality is still there in sort of a lot of the machine learning, trustworthy machine learning papers. They say, oh, but you don't know this. Well, what do you mean I don't know this? I can read your paper if I'm an attacker. And my last pet peeve is that we seem to have forgotten a lot of the lessons learned from a long time back. Let me give you an idea. There used to be a field called information hiding, which is less active now. The idea is that you embed a watermark in an image, and later if you claim that the image is yours, I can extract that watermark and prove to a judge that, no, this was my image. And there were a lot of proposals got broken. I think Ross Anderson's group was very active in this breaking some of the information hiding. And later people realized that, look, maybe this is not possible. And there are some impossibility results in that field. And guess what? I see a lot of papers that start using this idea of watermarking, and then they basically, are not even aware that there are some of these impossibility results that were published a long time back. So I will basically end with that. And I'm open to questions, especially, if you have comments, questions, whatever, I'm really open to that. And I'll also monitor chat now. Okay.
While we're waiting for people to formulate their questions, let me just lead a virtual round of applause here for the talk. and say thank you very much.
Thank you so much. It was a pleasure talking.
And repeat your call for any questions from the group.
Yeah, I mean, questions or comments, it doesn't have to be a question. We are not playing Jeopardy here. Everything doesn't have to be put as a form of a question. So any comments or on what we talked about?
So Somesh, let me ask here. First of all, thank you again for the talk. Your lessons learned, strike me as having some lessons, as you said, that we're learning in cybersecurity, kind of over and over again about obfuscation not being a great defense for all this. I think the challenge I'm seeing with machine learning here with the system being sort of in the code itself and kind of being distributed. Do you think we're in some sense making any progress on getting rid of obfuscation here, because the algorithms themselves are, at least in some sense, testable, if not always understandable?
Yeah, but I think I think my bigger thing was that when you do your security arguments, you cannot see, like when you do a crypto style argument, right? You assume that the attacker knows the algorithm, but there are some secrets like the key is left secret or something like that. You cannot assume your defense algorithm is completely like, oh, I'm secure because you don't know what I know, right? That kind of an argument, and that's what I was meant by security, by obscurity. Yes, there are some things like maybe there's a model randomization seed or something that is not known to me, but your actual algorithm, how you do your encoding, for example, should be known to me. You see what I'm saying?
Yeah. No.
And this is a basic tenet. I mean, this is something that even if you do an undergrad class in security, you will probably teach this, right? And what happens is I'm finding that a lot of the machine learning folks are, the training is very different. The training is more on optimization, statistics, machine learning. They kind of almost miss that training on the security side.
Agreed. Makes a lot of sense. Well, let me poke our audience here once again, and while we're doing that, just remind everybody, I just want to thank everyone again for attending another CACR speaker series this year. Please look for an announcement about our fall lineup, and please also look forward to us returning to being fully in person.
Oh, great. Yeah, that's much more fun.
Yes, our plan is, with everything hopefully cooperating, to have the speakers back here in the Bloomington campus in the fall, back in Beyer Hall, our Maurer School of Law, as well as our usual satellite locations.
Okay, great. Thank you so much. Thanks, Vaughn, for hosting me.
Thank you again, and thank you to the Luddy School for co-hosting with us, and thank you to everyone who's turning up. I will go ahead and adjourn the meeting at this point, and wish everybody a good summer, and we'll see you again in the fall.
Okay, thank you.
Take care, everyone.
Bye.